much for the introduction, and thanks to the organizers for inviting me and giving me opportunity to talk. Thanks a lot. It's a wonderful place. I enjoy very much being here. So this is a joint work with Alexandra Chatsi-Nikolaou, and Ivan Todorov. So Alexandra is from Greece, and Ivan has been here for 4 weeks and just left. So this is the outline of my talk. So first I will introduce what I mean by absolutely dilatable maps. I will consider them in the context of so this will be a completely positive maps, and I will put some modularity condition on these maps, and then characterize absolutely dilatable such model maps. I will show that there is a connection to factorizable channels and to quantum information theory. And having this connection also, I will discuss in the spirit of this result about factorizable channels, give dilatable maps and a connection to embedded problems. And then I will give some ideas. So I will formulate results first, and then give some ideas behind the proof. Okay, so let me just start with what I will have as an object. So I will have a M tau, so it will be a threshold von Neumann algebra. So this is a tau. This is a semi-finite normal faithful trace. So it's a map on positive elements of my von Neumann algebra to 0 infinity, including, so it can be infinite. It's linear on the cone of positive elements, and triviality means that it satisfies this condition. Faithfulness, so it means that whenever a trace is equal to 0 for some positive elements, so then it should be 0. And semi-finite, it gives me this condition, so whenever I have that x is non-zero, and maybe the value of tau on it is infinity, so then there exists an element y, so which is less or equal than x, where the trace is finite. Yeah, so we can think about so M as a bounded operator on a generally infinite dimensional space, and tau, this is the trace. So you'll say that tau is a trace preserving if I have two threshold von Neumann algebras. So then tau prime of the image tau of x, it should be equal to tau of x for all x positive. And so if I have a threshold von Neumann algebra, so I can associate a non-commutative LP space. So these are all elements in M for which the value of tau on absolute value of this x to the power p is less than infinity, and then I take the closure with respect to the clear norm there. And then L1, non-commutative L1, so it can be shown that it's isomorphic to the pre-dual of the von Neumann algebra. So if I have my B of h and I have my tau trace, so I will get these Chatin classes as P of h. Okay, so absolutely dilatable maps. So what are those? I have this threshold von Neumann algebra. So the definition was given by and Lemerdy in a recent paper from last year. So a map T from von Neumann algebra to itself is absolutely dilatable if there exists another threshold von Neumann algebra and tau prime. There exists a trace preserving normal star homomorphism. There exists a trace preserving normal star automorphism on this other von Neumann algebra N, such that if we consider t to the power k, so then I can dilate it and find a power dilation t of power k can be written as u to the power k, and then I have this stop-resolving homomorphism j, and I have E, where E is the condition expectation onto M associated with this J, meaning that we have the following equality. Okay, maybe I just write this the diagram. So what I have, so I have M, I have here the map T, so I have a J which acts to some other N. So here I have a star automorphism to N, and here I have back this conditional expectation. Okay, and I have here, so I can have a dilation of this.
You say this is dilatable, and isn't his definition already, I don't know, years ago, Clara de la Roche, she wrote it, and she calls it having a Roca dilation. But this is exactly this. I mean, she allows more general setup.
Yeah, she allows more general.
But if you have traces, then it's just the same. It's not important, but
I think she, okay, yeah. Yeah, so motivation for Duquet and Lemerdy to introduce such kind of map is they wanted to see a generalization of so-called Akoglu's dilation theorem to non-commutative LP spaces. And the theorem just says if we have a commutative LP space and we have a positive contraction, so then it can be dilated, so there exists another LP space instead of N here. And then isometry between those LP spaces. There exists a isometric map J, and there exists a contraction E, such that T to the power K, it would be like this dilation here. Yes, so also, so another motivation, so that in case of, at least when we have M being matrices, so there is this relation to quantum information theory, so which I will mention later on. Okay, yes, so what we have a remark first, that if I have such a map, so then this T is, it will be unital, normal, completely positive, and trace preserving. So with all these conditions, so we will get that T is UCP, TP, normal. Okay, so completely positive, you know what is completely positive, right? Yeah, so then we will be focusing on maps T, which are absolutely dilatable as maps from B of H to B of H. Okay, so, and what are completely positive normal maps from B of H to B of H? So we have a nice characterization. So there exist coefficients AI in B of H, such that the following sum is weak star convergent, and T of X is given by this kind of Krauss form. Okay, then we will need also modularity. So if I have D in B of H, this is a von Neumann algebra in B of H, we say that T is D modular. So if it's T commutes with left and right multiplication by operators from D. Okay, so if we have now that T is a unital, weak star continuous, completely positive D modular map, then we have the same representation as here, but the coefficients we can choose in the commutant of the algebra D. And if we ask for to be unital, so then we have that this sum should be convergent to the identity. Okay, so there exists, it's not yes, so there exists such decomposition where these coefficients AI are in the commutant. Okay, so if you have such T, Weeks are continuous UCP map. So then we can also talk about the symbol, so which I defined in the following way, and consider it as an operator in B of H tensor of H and call it the symbol. Okay, yeah, so the goal is try to characterize such absolutely dilatable D-modular maps on B of H. So if H is finite dimensional, so Hagerup and Mossad, so they characterize such a map on when D is equal to just C. And when D is L infinity or massa, so Duque and Lemerdy, that was their main result in this paper from 23. Okay, and we did it more general, so and the result, the characterization is the following. So if we have a T UCP map and D is our one-Neumann algebra, then we have that it's convenient to change D modularity to D prime. So D prime is just the commutant. D is D prime modulo absolutely dilatable. So if we have now we have a normalized threshold, so Y-net threshold of von Neumann algebra, n with tau n, so we call it ancilla, and a unitary D, so it will be an element unitary in this tensor product D tensor B of H, which satisfies such that T of X, it will satisfy, it will be given in as this slice. So we take X tensor 1, so we conjugate with this unitary D, and then slice with respect to this trace tau n. In order to have that this would be the well defined, so that we can define the slice, so we have the condition so that this product, so this is just the leg notation, so D23, so means that it acts as D on here, and it has identity on the first component, and D13, so it has legs in D and this N. And we call that D returns to N. So in general, so we don't have ideally it would be that we get the D is in the tensor product of this algebra, von Neumann algebra D and this ancilla N, but yeah, so we have only this condition in general. Yeah, and then having this, so you'll have the symbol so of this map, so it can be written in this way. Plus certain conditions, so that there exists some vector in H such that this would be equal to 1. Okay, so as I said that if H is finite dimensional and D general, so it's just the complex numbers, so no modularity. So that was done by, this was proved actually by Hagerup and Mossad. And there they could choose this unitary D in here, so this D tensor the ancilla N. And also Duque and Lemerdy, so they could also find their unitary D, which would be in this algebra. And it's quite easy to see how one can fix this D in this particular case when D is massa. Yes, so if we have the T from a matrix algebra, and this is a metric algebra, is absolutely dilatable, so then we will get that this would be actually a quantum channel, so it's trace preserving UCP map. So then it is absolutely dilatable if and only if T is factorizable in the sense of Anand-Sarman de la Roche, and meaning that T can be splitted in such a way where alpha and beta unital star monomorphism from matrix algebra to matrix algebra tensor N, where N is some normalized threshold. Okay. Yes. So so from the proof, one can see the following, and we will have an opportunity to see this. That if T from B of H to B of H is absolutely dilatable, or it is absolutely dilatable if and only if it is dilatable of order 1. So if we have this dilation here for each, so we ask, when we ask about absolute dilation, we ask that for any power k, so we have that u such that t to the power k, it will be such a product here. So u to the power k, j, and e. So this statement says that we will always arrange u in such a way. So even if we ask for just n equal to 1, so we can always arrange so there will be a power dilation, not only a dilation of order 1. Okay, and then yeah, so one can ask whether there exists non-absolutely dilatable or non-factorizable map in the case of Mn. And this is the result of Hagerup and Musad saying that there exist non-factorizable unital quantum channels. And this result was important also for, in the quantum information series, for resolution of the asymptotic quantum Birkhoff conjecture. So even in small dimension, as n equal to 3, so there exist non-factorizable, which in this case is absolutely non-absolutely dilatable maps. Okay, then one can ask about special maps. Not all maps, T from B of H to B of H, but maps which comes out from so-called Schur multipliers. So we want to know, yeah, what would be absolutely dilatable Schur multipliers. So what is a Schur multiplier? So in a discrete case, in classical case, so this is a function phi on the product, Cartesian product of x. X is just some set, so it can be finite or infinite to C. So it's a Schur multiplier if whenever I have that this is a matrix of a bounded linear operator on L2 of x, then after multiplying this pointwise AXA by the value phi of xy, so I will get a matrix of a bounded operator. Okay, so then having this, so it's easy to show that the map which sends this matrix into that matrix, it will be a bounded operator. So then we will get this map as phi, so which doing this, this will be a bounded operator, and it will be moreover L infinity modular map. Okay, yeah, so if S phi is unital and positive, and in this particular case, since it is a massa modular map, so it will be automatically completely positive map. So we have that the symbol of this map, which is exactly this function phi of xy, so it can be written in such a way. So there is this factorization, so Grothendieck's factorization, so that there exists a function a from x to some Hilbert space h, having this property so that the supranorm of the norm a of x, h norm is equal to 1. And phi of xy, this is the inner product of these two vectors in h, a of y and a of x. Okay, and so if we see what would it mean for S phi to be absolutely dilatable, so having that characterization or characterization by Lemerdy and Duquet and Lemerdy, because they consider it exactly L infinity modular maps. So we will have that S phi when we act on EXY, so it should be such identity, the slice by trace. Here we will have this conjugation by unitary, which is in the L infinity tensor some ancilla n. So we can write it in this way. So meaning that phi of xy, so if we write don't what it is, so then we will have that phi of xy, so it will be equal to this trace d of x tie d of y, and d is just the unitary from this ancilla von Neumann algebra n. Okay, so having this, we can rewrite it in this way, like it is here. Okay, so looks similar. So the only difference, so here we have special Hilbert space and special function, not just arbitrary function. Okay. Yeah, so one can ask the question whether, okay, so whether any Schur multiplier yeah, so would be absolutely dilatable. Okay, whether we can always find another representation. So of course, this representation is not unique. So whether we can find a representation of phi in such a way so that it can be written in this way. And it's also done by Uffe and Magdalena. So they found a non-factorizable map S5 in high dimension from M6 to M6. So it's again, so even in smaller dimension, so we can find Schur multipliers which are unital and positive, which are not factorizable or unitally dilatable. Okay, so yeah, so I said that, yeah, we had, I already named that factorizable maps Uffe and Magdalena used to prove this or disprove the approximate Birkhoff theorem. So, but also they appear in the study of correlations. So if we have some finite set x, y, and a, b, so we have this p and on signaling correlation with, so meaning that we have that this well-defined marginals. So one says that p is bisynchronous if whenever, so if one think about the game, so whenever Alice and Bob get the same questions, so they have to answer with the same A, B. So in order to win, so the probability to give the answer A, B, where A is not the same and B is equal to 0 when they get the same question X. And they have two different X and Y should give also different answer A and B. Okay, so to such bisynchronous correlations, so one can, or in general, so to correlations, so one can associate a map Fp, which is given in such a way, so it will be a quantum channel. Yeah, and yeah, so I use this notation CT to define classes of correlations. So we talk about this many times about classes, and the theorem of Verne and Mizo-Rahman from 21, so gives a connection between these bisynchronous correlations and factorizable maps. So we have that this correlation is in the class QC, is bisynchronous if and only if there exists an ancilla n with a trace tau, such that PAB twice is equal to this one, where PAX, this is a quantum permutation in this PAX in N. And this is also equivalent that this quantum channel FP is factorizable, but factorizable with respect to special unitary, so it's factorizable with quantum permutation P. So we have this stuff. So this is kind of connection to quantum information in a finite dimensional case, but we don't know whether there is some connection in infinite dimensional. Yeah, maybe. Yeah, so one can give a similar characterization for classes log, Q, QA. So for example, if we have here log, then we ask for ancilla to be abelian. So if we want to have Q, so then we ask this to be finite dimensional. QA, this is the ultra power of hyperfinite 2-1 factor. Okay, so yeah, so then our general absolutely dilatable map. So we can also define different classes depending on this ancilla which appears in the characterization of absolutely dilatable maps. So we say that this T is locally factorizable. So if we have this ancilla n is abelian, and we write it in this way, it is quantum factorizable. If we have a finite dimensional ancilla, then QA approximately quantum factorizable if it's if n is embeddable into matricial ultra product. And we also, just to have a similar notation, so we write this one for T, which is absolutely dilatable. I also will write T x here. So if we can choose the corresponding unitary in this D tensor ancilla n. So in general, so we have the D, this unitary is in D tensor B of H with certain condition, but if we can choose it here, so then I will put this X there. Okay, yes, so again back to absolutely dilatable maps from Mn to Mn, and especially Schur multipliers map. So if we have this T, which is absolutely dilatable, so then we know that the symbol phi, so it can be written in this way where di is a, it will be a unitary operator for each I. Okay, so one can consider such sets Gn, so which are given in this form. So this n, Tn, so some ancilla, and here di are unitary. And if n is finite dimensional, so we get the set G fine n. And if ancilla is abelian, so we get this set. And the relation to Cohn-Simbelian problems is the following due to Kirchberg, so that CEP has positive answer if and only if that this Gn is the closure of G phi n, all n larger than 3. So therefore, somehow it's kind of motivation why we want to consider these different classes. Yeah, some properties of this set DT D. So if yeah, so we consider for simplicity separable Hilbert space. So then one can recognize certain statements. So like from correlations, from the similar properties of correlation sets. So that if we have for T in these classes, so the set DTD, and those sets are all convex. Then we have that log class and QC class when we have the exact class, so they are closed in point fixed topology. We have also that QA class, so this is the closure of Q class. And we have that, yeah, if we have the ancilla is abelian, so then we can remove this X, it will be, we will have the equality, and actually this class is the point fixed closure of automorphism of B of H, which are also D prime modular and which are just conjugation of by a unitary operator from D. Okay, yeah, another theorem, so which also, yeah, similar to things which we have about correlation sets. So if I have a D is a massa of dimension larger or equal 11, I will explain later why by 11. So then we have the following inclusions, so that D log intersected with DQ, so it sits in DQ in a proper way, so they are not equal. So we don't know whether D lock is sitting in DQ. So like in one has for correlation. Yeah, so here we have H. Yeah, if H is finite dimensional, so we do have that, but when H is infinite dimensional, we don't know whether D lock is sitting in DQ. And then DQ sits in DQA is also proper. And then we also, if we take this so like L infinity 0, 1, so the Cohn's embedding problem is equivalent to the verification of this DQA is equal to DQC for this particular algebra D L infinity 0, 1. Okay, yeah, so this result, and now I want to give some ideas behind the proof to our theorem, so our statements. So what we yes, the statement says the following. So if I have the T from B of H to B of H is absolutely D prime modular, so then T of X can be written in such a way. So where D is some unitary here, and which has the properties which returns to n, meaning that so that the condition which gives us that this product, it will be actually in B of H tensor this ancilla n, so that we can take the slice by tau n. Okay, so this was the picture, which is also there. Let's assume that we have this diagram. So we have our map T from B of H to B of H. And we can dilate it. And I don't ask about power dilation, just the usual dilation. So there exists U, normal trace preserving star automorphism from M to N. So there exists some von Neumann algebra M with semi-finite trace. So J is a unital trace preserving normal star homomorphism from H to M. And we have that E, this is the conditional expectation related to J. Okay, so how we can get such factorization? So we want at the end to have this characterization. Okay, so what we do? So we take a matrix unit system in B of H, constructed from the orthonormal basis in H. Then we have that J. So this is a star homomorphism and trace preserving. So we have that J, U, E, I, J. So E, I, J, so just the matrix unit. So just the, So we'll have that this would be also a matrix unit system in this algebra M. Okay, so I fix some index and call the image of this projection by Q, and get the trace preserving star isomorphism from this M to the tensor product B of H, Q, M, Q, which is given in such a way. So it sends M. Then we consider Mij, so just take this product here, and then put Eij. So this would give me a star homomorphism, and it will be trace preserving. Okay, so therefore, so we can go to, we have M, we have B of H, T, B of H, and instead of M, so of this ancilla, so I can think about B of H tensor N, B of H tensor N. So my G, so it will be just sending X to X tensor the identity. And here, so I will have that this is just a tensor tau n. Okay, so next, yes, so I have this unitary U, oh yeah, normal star, not unitary, star automorphism U. So, and I have that this would be also matrix unit. So when I apply U, so I will get a matrix unit system again. And this would, in the same way, so it will give us the trace preserving star isomorphism from B of H tensor N, so where we are now, to B of H some other N1. And actually, so it will send, since it's sending here Eij to Eij tensor 1, so it will send any element Z to Z tensor 1. So we will have that pi U Z tensor 1, so it will be equal to that one. Okay, then also it's not just the star isomorphism, it's also unitary, it's a spatial star isomorphism. So this pi, it will be given by conjugation by some unitary operator. Okay, so then we will get that U Z tensor 1n, so it will be just conjugation by this unitary operator D. And we will get this, this presentation. And then when we apply some modularity, so we can fix that D is in the right space. Okay, so this is in one direction. The converse. So let's have that T of X has this presentation. And we want to see whether T is a power dilation of a star automorphism. Okay, so we want to find U such that T and J and E, so such that T to the power K, it will be E, U to the power K, and J. Okay. So we cannot take U as this conjugation by D, because if we take T to the power N, so yeah, so when we just make a calculation, it's not just D to the, it's not the power of this conjugation by D. It's not just D to the power D, N to the power star, yeah, D, N. So it's something different. So we have to choose our star automorphism U in a different way. Okay, so how we construct it is the following. So we know that this unitary D, so it's special, so it returns to N, which means that if I take D star B of H tensor 1 D, so it should be in B of H tensor N. So in other words, so B of H tensor 1, it should be in this space. Okay, so in B of H we have matrix unit system, so it gives me a matrix unit system in this algebra. Okay, so having matrix unit system, so then we can construct in a similar way a trace preserving star automorphism gamma from, so I will write in this way, so B of H tensor M to BH tensor N. And gamma, it will be given by conjugation by some, and this gamma, it will be given by conjugation of by this unitary D. Okay, so now how I construct my algebra Mn here, so I will denote it by this frac M. So I consider the following, so I consider the infinite tensor product. So I put B of H. I have M minus, so this is the infinite tensor product of the same M. I have M, I have my N, and I have N plus, so it's also infinite tensor product of N's. And I take tau as a product space on this tensor product. Okay, so and I say that this would be a disputable ancilla which appears here. Okay, so how do I construct my star automorphism? So I consider such creation annihilation operator probably. So sigma minus from m minus to m minus tensor m. So I just given in this way. So this shift. And sigma plus from n plus to n plus, which is given in this way. And then I define my U, a star automorphism U from this M to M, which is given in such a way. Okay, so kappa 1, so what does? So it exchange B of H and M minus. So it moves B of H to M. I have my B of H and minus M N plus. So I apply first kappa 1 and get to M minus B of H tensor M. So it's just a flip. N plus. Then I apply my sigma plus, and I will get into B of H M, and I will have here N plus. Okay, so I collapse this one into N plus, and then here I apply my conjugation by D on this, and I will get to M minus BH tensor N and N plus, and then I apply sigma minus and get to B of H N and N plus, and then I move back B of H. Okay, so this is conjugation by. Okay, so doing this, so I will get that this will be the right map. Yes, so and I will get that actually t to the power n, it would be exactly this, what I wanted. So g is sending x to x tensor 1, so it should be. So e, so it will be just slicing by tau, and one can check that t to the power n will be such a form. Okay, so this is the main statement. Then about closeness of such classes. So here the classes are defined by so this is absolutely dilatable maps, which has the exact factorization, so meaning that the unitary are in the D tensor, the ancilla. So if I have such a map, phi n, and so it's written in this way, where dn, it will be D tensor ancilla, and I have that fn goes, x goes to phi of x, weak star. So I have my dn is here, so it's unitary, and this is a normalized three-shell von Neumann algebra. So then I construct a ultra product of these n's, and yeah, construct another d tilde on this here. So as a operator space is the same as completely bounded map from d star to n tilde. And then if I have d tilde, so I will get completely contractive map from d star to n tilde. And then I can factorize and get contractive map to n. And then we'll get contraction in D tensor n, such that phi of x would be of this type. And then if I have the condition that phi is unital and trace Preservian, and since tau is faithful, so I will get that this would be actually unitary. Okay, and just a few words about properness of inclusions. Yeah, so that this inclusion is proper, so follows from the result of Hagerup and Mossad, so which constructed as phi non-factorizable through finite dimensional ancilla, but is not in the convex hull of automorphism of matrix algebra. And then one can lift it to general H, this result. And then that this one is proper, so follows from another result by Mossad and Roerdam about the existence of factorizable map from M11 to M11, which is a limit of factorizable maps with finite dimensional ancilla, but does not admit the finite dimensional ancilla itself. And this is based on Varn's result about construction of no-signaling synchronous correlation in the quantum approximate class, which is not quantum. Okay, yeah, I think this is the end, and I happy that I have some time also for my last slide. Yeah, I show it now at each conference. It's about the International Center for Mathematics in Ukraine, so which we created almost 2 years ago. So yeah, so the goal is just to get much more benefit to mathematical community in Ukraine, especially in this tough time we have in the war. So we have we cannot do much at the moment, but still we have run some programs, and we organize some summer schools and winter schools. One of these schools we organized together with Adam this summer in West Ukraine. So exactly almost the same title of operator algebras, quantum groups, and quantum information theory. And Jacek was also with us lecturing. Yes, so we have also some programs like London Mathematical Society is helping us, and we have something which is called LMS Distinguished Lecture. So people also come to Kyiv and Lviv and lecture for students and mathematicians which are in Ukraine at the moment that cannot leave the country. Yeah, so this is a picture from our inauguration conference, which was on 2 grounds, one in Warsaw, and Adam was one of the organizers, and the other one was in Ukraine, and we had like Marina Vezovska was lecturing in Kyiv, and Terence was lecturing in Warsaw. Yeah, so we have a scientific board, so these are pictures from our scientific board. We have quite famous people in there. Yes, we have Efim Zelmanov, we had Vladimir Drinfeld, we have Peter Scholz, we have Rostislav Grigorchuk, and yeah, we have Adam also, a member of the scientific board. Yeah, so of course we don't get any support from Ukraine, from Ukrainian government. Of course, not the priority. So mostly we rely on some grants and donation. So, and the point why I want also to show this, yeah, so first that you know about this center so that you can spread the word about it, but also if you know someone so that somehow can help the center, yeah, or if you want to organize one of those schools, of course it requires some courage to come to Ukraine now or to lecture within this program, LMS program. So you are very welcome. You can ask me about things. You can ask also Adam, so he knows many things about the center. Yeah, thank you.
Questions?
Maybe I have a quick question about this. The very first theorem you showed us, when you said that, well, in finite dimensions or for massa, you know that you can achieve that this unitary is actually sitting in the tensor product.
Yeah.
Right? So do you know that in general it doesn't have to be the case? Or
We don't know. We don't know any. We don't have any example now. So if ancilla is commutative, so we can remove this. And, yeah, not quite completely trivial, but still, so it could be removed. But in general, we don't know.
Why does the local set end up not necessarily being in the quantum set?
Yeah, but this is an example which Musat and her group have.
Well,
so
you said it, not the separation, but why is not contained inside?
Yeah, because they're in Q case, so this is kind of very finite dimensional, and yes.
So would it be okay to add like anything infinite dimensional but abelian to the quantum set? That maybe it wouldn't change it being quantum in the sense that it's just the finite dimensional, the non-commutative part is finite dimensional.
Okay. Yeah, maybe. Yes. So then this case could be.
And is the local part inside the quantum approximable part?
Yeah.
Okay.
That's.
Last chance for any other questions. Now we'll thank our speaker again.